Hello and welcome back. In this video, I'm going to discuss some of the math behind the gradient descent in linear regression to give you an idea about what the calculations look like. And this could be a complementary video to the code switch video that we did earlier, where we try to write code from scratch to perform gradient descent for linear regression in TensorFlow, Kotlin, Python, Scikit, Base Python, and Keras. So let's get started. And if you like these types of videos where you get some mathematical intuition, please do let me know in the comment section below, and I'll try to create more videos of this type. So let's start with a simple line. So let's say we have planes X and Y, and on this plane we have a couple of data points like this. What we can do is, let's say if we are in a situation where we have a new data point that is right here, and if we want to find the corresponding value of y for this data point, how do we find that value? Because to find the value of this new data point, we uh, we we could say that the value is this, or we could say that the value is maybe this value, or we could say the value is this value, right? So we do not know what should be the value of this new point, and therefore what can be done is we can try to fit a line. We can try to fit a line. What that means is we try to find infinite number of such data points that go through this particular cloud of original data, and this particular line that we find is called as a model, or you could say this line was fit to the original data, and how do we find this line? Well, to find that line, we could start out with a initial line could be like this. Then the next line could be like this, or like this, or like this. There are infinite possibilities, and the final optimal line that we would choose would have one thing, and that is the error is lowest. And when I say error, it is how far is the original data point from a point on that line. For example, if we look at this data point right here, this data point is at a distance, this distance away from that line. So this we can think of as the predicted value, and this is the actual value of that data. This is the actual value, and the predicted value is shown here by the gray dot, and this height is the error. That's the error in predicting that point that we have up there in blue. So this is the error, and this error exists for all the data points. So in this case, the error is that distance. In this case, the error is this big. In this case, the error is right here, and up to here. So the point is that the best line that we have would have smallest of these errors that we see, and thus we can so that's the part of finding the best line. Now what we can do is we can represent the line that we just saw by an equation. So we can represent this line by equation of a straight line, which is y is equal to mx plus b, where m is the slope of the line. Slope means how slanted the line is. So in this case, that's going to be the slope of the line. B is the intercept of the line. Intercept is the height on y where the line intersects the y-axis. So this is going to be the B. Now, when we say in machine learning, when we say we are going to train a model, when we say we are going to train a model, or when we say we are trying to fit a line, what we are essentially trying to do is we are in a cyclic process where we try to start with some random values of m and b and try to predict values for y for any given values of x, and we then measure what the error is, and based on this error we again update the values of m and b, update the values of m and b, and then go back up and predict and see what the error is. And that's sort of the cycle where we are trying to uh, find the best fit for the line. And let's say in this case, if we find the optimal values for m and b, let's say the value of m is 1 and the value for b is also 1. In that case, our final model is y is equal to x plus 1. Now with this equation that we have now is the model. So that's the model we have built. You may ask, well, what's the big deal about finding equations such as this? Or why do we even care about such a model? The reason is that if we can use this model to find values of y for any value of x that is not present in the uh, original data set. For example, if we have a value of x that is somewhere here, and if we try to then find the value, corresponding value. So let's say we have a value of x, we have a value of x somewhere here, right here. And then the corresponding value of y is going to be right there. So what we did just now is we had a new data point for which there is no the new data points are, of course, that does not exist in the original data set, but it is still in the range of the original data points. And so we can now walk up to the line and see what point we are, and that's going to be the value of y, and that's the predicted value of y. So we can use such a model to find new values of y, and that's when we say when we find new values of y, we are essentially trying to predict the values of y. And of course, when we make such predictions, it is always with some level of some margin of error. And if our model is a good fit, this margin of error is going to be much smaller. Let's now see what happens if we choose some values of it. Let's say if we are trying to find a value of y, if when the value of x is 1. So the value of y is going to be 1 plus 1, that is equal to 2. Likewise, if we change the value of x is equal to 2, then what we would have is the value of y is going to be 2 plus 1, that again is going to be equal to 3. And thus we now have a easy way to find values of y for any given value of x. The only thing to remember is that the values of x need to be in the same range in which the original data set is. If we try to go beyond this range, then the values of y that we find may not be reasonable. So that's the sort of the background story about the linear regression. Now, you may ask, where does gradient descent come in? The gradient descent comes into play when we are trying to find these values of m and b, right? So, and to do that, what we need to do is reduce this particular error. And to reduce the error, we need to update the values of m and b. And we do that, we update these values by either adding or removing small values from this particular existing current values of m and b. And that's where gradient descent comes in, where we which helps us to find how much should we subtract or how much should we add to the existing value, and what direction, that tells us what direction the values of m and b should go. Here, if you were to try and plot this error, so the error that we are talking about in linear regression, what we do is uh, we we can formally write this equation that we have, which is y is equal to mx plus b. This is the one that we saw, but in terms of machine learning, we write in a different symbols, let's say. So we would write this as y I. So I just represents number of samples. So let's say, imagine that you have a data set, and in the data set we have the value of y, which is the target value. And let's say here are the features that we have, and let's say in this case we have 1, 2, and 3 features, right? 3 features. Now for each feature we have a couple of data points. So let's say here we have 1, 2, 3, and maybe the y value is 0.1, right? So this is going to be one data point. This is one data point. Likewise, we would have another data point here. And for this, let's say the values are as we see here. So this is going to be our second data point. If we have another set of values, as you see, maybe in this case, the data point, this would be the third data point, and so on. The data set essentially then could have hundreds or thousands of such data points, right? So how do we represent these data points in mathematical notation? That's the question. So what we usually do is, here for y, we are simply using the letter I. What that I represents is, for the first data point, whatever the value, original target value of y is, it will be 1. Then for the second one, it will be 2, second data point, and then the third data point, the value would be 3. So that is what this I represents here. And after that, we are going to move things around. We are going to represent this b by beta 0, and that is the intercept, just as we saw previously. After that, we are going to add another value, which is beta 1. Beta 1 is going to represent the slope term in this simple case, where we just have, let's say, one feature. And this feature again would have I next to it, because let's say if we just have one feature, then x of 1 will represent this value, x of 2 would represent this value, and so on. Okay. Now, if we had more than one feature, just as we see here, then the equation that we would write is going to change a little bit. We would still have y of I, we would still have the beta 0, and after that, we would have some additional terms. We would have beta 1, that is as before. And then instead of I, we are going to have I1, because this I represents the data point. Here 1 is representing the feature. Likewise, we would have, for the second feature, we would have beta 2, and with this we would have another x. Again, we would have I, that represents what data point it is, and 2, that represents that it's the second feature. And finally, let's say if we have 3 features, then we would have a third beta, which is beta 3. Again, this would have accompanying accompanying xi with 3 written to represent that it's a third feature. So that's how we can see that each feature, is represented by a single beta that is applicable to all the data points that are there. So there's that's something to remember. Now, in this particular example, what we are going to do is we are going to stay with our just one feature setup, just so that it's easier to explain and easier to understand the concept. Now, when we look at this equation, we are going to say that this equation is where here y is the predicted value. So we are going to say that y is the predicted value, and we could show it by a cap on top. And again, this other part beta 0 plus beta 1 xi, it will stay as is. And when we talked about error earlier, so this error term, what error is simply the difference between the actual value and predicted value, just as we saw here, the red line that we saw. So to represent that red line mathematically, what we are going to say is that the error is nothing but the difference between the actual value of y minus the predicted value of y, and the predicted value we are giving by y hat of I. So that is the error term that we have. Now, in linear regression, what we usually do is we square the value of error. So we square the error term, right? Error term is squared, and so so to square the error term, we simply are going to get the difference between these two and then square it. What squaring does is it uh, it gives us the magnitude, and so all values are positive. That's one one change that happens with the error term. So let me just write it clearly. This would be 2, so that's the square term. Now this if we are trying to find the best line, what we need then is an error term that is lowest as possible. So we need to add all the errors, and to add all the errors we are going to sum them up, and therefore we need to put this summation sign here that goes from I is equal to 1 to n, so all the errors. And this is what we call as sum of squares. So this is what we call a sum of squares, and therefore we can represent that by SS. And ideally though, the term that we use is called as mean of sum of squares, and that can be calculated, or it is represented as follows: MAC, mean squared error, and that is equal to the same equation that we wrote above, which is nothing but the difference between the actual and predicted value, square of that and sum of that. So I'm just going to write that down over here again. And we are going to, because this is a mean, we need to divide this by the total number of samples. And so we are going to multiply this by 1 by n. That is the same as dividing this sum by n. So this is the mean sum of squares, and that is the main equation that we can use along with the gradient descent to find optimal values of beta. And if you're wondering, well, how would you find beta values if there's no beta in this particular equation? We can do that by simply substituting the values of yi. And to do that, we can proceed as follows. We can say that MSE is equal to, sorry, the pen is working slowly, therefore I have to write a bit slow. MSE is equal to, this is going to be equal to 1 over n. That we already know that this is going to be 1 over n. Then y summation of I is equal to 1 to n, and then we have yi is equal yi minus, so this is yi minus, we substitute the equation that we have above, so this is going to be beta 0 minus, then we have beta 1, so we write that down, beta 1, and then we have xi, so we write the xi next to it, and this is again the same square term outside. So that's the equation that we have, and this equation it is also called as the loss function. So this is also called as the loss function, loss function, or this is also called as the cost function that we can work with. So this is what we use to then calculate the gradients. And before we talk about gradients, I just wanted to share with you one plot. So if we look at the plot, so let's see if I can pull it on the screen. So here we have the plot. Let's let me find that. Here is the plot, and if you can try to create the plot. Here is the code for that. You can pause the screen to look at the code. Essentially, we are just creating some random values of x and y. We have a function which is the same as what we saw just now. It calculates the MAC, mean squared error, and then we have random, not random, but we have values of for beta 1 in the equation that we saw, and then we calculate the loss for several values of beta 1, and in this case for beta 0 we are saying that the value is kept at 4. That's the y-intercept we talked about. And if you try and plot this, this is the generic U-shaped curve that we get for a loss function that we are talking about, which is the MAC. Y-axis we have the MAC, x-axis we have beta 1. Now, when we are in the code, when we start out with our beta, we could start out with a beta, let's say, of 6. If the value of beta is 6, then our MAC or loss is somewhere here, right? And what gradient descent allows us to gradually make a little change to this beta value. So maybe in the next iteration, the beta could be slightly less than 6. Maybe it is 5.8. And if it is 5.8, then this time, maybe the loss function, the MEC that we get is slightly lower. And so we essentially moved one step down here, and our goal is to reach this point, which is the minimum which is the minimum error, right? The smallest error that we have, or the smallest MAC that we can get, is when the value of beta 1 is 3, right? So that's where we want to reach. And so what gradient descent helps us do is step through this particular process of finding the beta, updating the value of beta, such that we are reducing the MAC as we go. And so if the values are very small, then the updates can be tiny, and it may take a longer time to reach the minimum. If the updates are too large, then that may or may not be a good thing. So if the updates are too large, for example, the jump is here, the jumps could go like this, and that could become a problem. So finding the optimal value to change the value of beta is also important, and how fast or slow you want to change the value is also determined by something called as learning rate. And all of this, we are going to see how to do all of this in the calculations that we are going to look at right now. So let's look at the code that we and the text that we wrote here. Now, the step after this is, before we can do any of the gradient descent calculations, we need to perform the we need to get the gradients, or we need to get the derivatives of this loss function. And to do that, we can create a new page, and we can start calculating the derivative. So first, I'll just simply write the MAC equation that we have, and that is equal to 1 divided by n, and then we have the summation I is equal to this is 1 to n, and then in here we have the value y yi, which is the original value, minus, for predicted value, we said that we would put the values of beta 0 and beta 1. So that's the equation that we had written in the beginning. So this represents the actual values, predicted values, and then we square these. To calculate the derivatives, first we need to we'll take a derivative with respect to beta 0, and so our derivative is going to be partial of MAC with respect to beta 0, that is beta 0, and that is going to be equal to 1 by n, and here we take a partial of partial with respect to beta 0, and this is for this entire thing. This is I is equal to 1 to n, and then inside of this we have the same equation, yi minus beta 0 minus beta 1 xi, and we square that. And when we take the derivative, this is going to move in the front, and so what we would have is 2 divided by n, then we have partial of 2 divided by n, and then we can write the rest of it. This is going to be I is equal to 1 to n, and then inside of the parenthesis, when we perform this operation, we would have a 2yi minus beta 0 minus beta 1 xi, and so the 2 goes down there, and then then we find the differential of the terms that are inside it, and these would be 0, and all we are left with beta 0, and that will come out as -1. So we can rewrite the equation as -2 divided by n, and then the rest of the term stays the same. I is equal to 1 to n, and in this we would have yi minus beta 0. This is beta 0 minus beta 1 xi. So this is the value that we have, or this is the equation that we have uh, to compute this particular derivative, which is for beta 0. That is partial of MAC with respect to the partial of beta 0. And that's the first equation. That's the first equation we have. Likewise, we can find the partial with respect to beta 1. And for that, again, we would use the same equation. Partial of MAC with respect to this time beta 1 is going to be equal to 1 divided by n, and here we are going to take a partial with respect to beta 1, and so we have the beta 1 here, and the summation term is going to be the same, where we have a I is equal to 1 to n, then we have yi, this is yi, minus beta 0 minus beta 1 x of I and square of this. So this time when we are trying to take the derivative with respect to beta 1, the first term would be, the first part would be the same. These two we would get 2 by n, and then we would have the same term that we have seen before. We have I is equal to 1 to n, then we have yi minus beta 0 minus beta 1 x of I, and in when we take the derivative of the term inside of this with respect to beta 1, we just have this term where this would become minus of x of I, because the derivative of beta 1 with respect to beta 1 would be 1. And so we get minus x of I. And together, this the final equation for the derivative of MAC with respect to beta 1 becomes as follows. So this is going to stay beta 1. This would be minus 2 divided by n, the summation of I is equal to 1 to n, and then in parentheses we have yi minus beta 0 minus beta 1 x of I into, so that is going to be into x of I. And that is the second equation that we have for calculating the derivative. So these are the two equations that we are going to use to calculate the gradients. Now, in these two equations, when we are saying gradient, we can also write this as follows. We can say gradient, so we can say gradient is equal to, we can say partial of MAC MSE with respect to beta 0 and then comma we have the second one, which is partial of MSE with respect to beta 1. And so if we try to put these two equations inside of this, we could take the minus 2 by n outside, and then we have what we have in here is summation of I that goes from 1 to n y of I yi minus beta 0 minus beta 1 x of I. That's the first term, and then the second term is going to be summation of I is equal to 1 to n. Then we have y of I minus beta 0 minus beta 1 x of I, and outside of the parenthesis we have the x of I again. So that is the equation that's the final vector we have for calculating the value of that's the gradient that we have. Now if we try to implement this in the code, the way we have done this is we have taken the value of so gradient is equal to we have the train which is going to, so we have minus 2 by n, and then we have x underscore train. So that's the matrix we have for the matrix of features, and then we take a transpose of that, and then we dot that with the error term that is there. So the error term, I'm just going to write error. Okay. So this is going to be the this is the implementation that we have seen in the code. Now what we are going to do is we'll try and see if we can perform the same type of gradient calculation right here manually using a very simple example. And for that we will use an example. So if I'm looking sideways, that's because I have already worked this out. I'm just trying to refer to the example. So the example that I have is this. We have x is equal to which has values of 1, 1, 1. That is for the intercept. That's the beta 0. That's for the beta 0. We have put the values of constant term there, and then we have the values of the feature, which is 2, 3, and 4. Okay? So that's our x train, and then for the target, which is y, we have the target, which is 2, 4, and 6. These are the values for the target. So this is the original value. Let me write this down. This is the feature matrix that we have. This is the target, and here this is the constant term that's going to that we are going to use, that we have introduced, and that's our one feature that we have. So with this, we can now get started with calculating the values for calculating all the values. And one more point that we need here is we need a value of like the starting values for beta 0 and beta 1, and we are going to represent that vector by theta. and we are going to say this first value is beta 0, the second value is going to be beta 1, and to initialize the values, we are simply going to initialize the values by 1. So we have theta is equal to beta 0, beta 1, and both of them have a value of 1. Again, as I mentioned earlier, we also have something called as a learning rate, and that is how fast or slow do we want to change or update the values of beta? Do we want big steps or smaller steps? And that can be changed by this alpha parameter, and we will set this value in this case to 0.01. So that's the learning rate we have. So with this simple example, let's now try and see if we can calculate the values if we can calculate the predicted values, error term, then updates to the beta values. So in the first iteration, let's change the color. So this is our first iteration. So in this first iteration, we first start out with calculating the values for y, predicted values. And to represent that, we have the y and we have y hat. And we are simply going to put x dot theta. And that is the same thing as what we have seen earlier in the equation, except that because this is a matrix, we can do sort of vectorized calculations. And here then we have x, which is represented up above, which is 1 1 1, that's the constant, and we have 2 3 and 4. And after this, we are going to dot this with the theta. We currently have the values of 1 and 1. And as you may know already, the way the matrix calculations work is if we have this matrix, which is 3 by 2, and this matrix, which is 2 by 1, then the resultant matrix from this calculation would be of the size 2, it's going to be of the size 3 by 1, right? And that makes sense because we have three data points, the first data point, second, and third, and so we would expect three predictions. So this would then become, this is going to be equal to 1. So I'll do the first one. So 1 multiplied by this one, then we have plus 2 multiplied by this one, and 2 multiplied this one, and so that comes out to 1 plus 2, which is 3. The next one is going to be 1 multiplied by 1 plus 3 multiplied by 1. And so that becomes 1 plus 3, that is 4. And last one is 1 multiplied by 1 plus 4 multiplied by 1. And that becomes 1 plus 4, that is 5. So in this case, our predicted values are 3, 4, and 5, right? So 3, 4, and 5, these are our predicted values. Next step then is to calculate the error. And so let me write it down. So y hat, so this is the predicted, these are the predicted values after first iteration with this initial values of beta 0 and beta 1. And we can see how far they are by calculating the error. So if you try and calculate the error, we know that error is simply going to be the difference between the actual value and the predicted value. So the actual value that we have is 2, 4, and 6. And the predicted value that we have is 3, 4, and 5 that we have calculated above. And so the error that we get is going to be, the error that we are going to get is 2 minus 3, that is minus 1. 4 minus 4, that is 0. 6 minus 5, that is 1, and so on. So once we have the error term calculated, we can then calculate the gradients. And as you know that for calculating the gradients, we are essentially going to dot the features with the this particular error term. And let's do that. So gradient is going to be equal to minus 2 divided by n. In this case, we have 3 data points, and so we have value of 3 as n. And then we are going to take a transpose of x and then multiply that with the error vector that we have there. And so this is going to be equal to minus 2 divided by 3, and the error term that we have when we transpose it, the feature matrix, when you transpose it, it's going to be 1 1 1, and we have 2 3 and 4, and after that we dot this with minus 1 0 1. So and now when we perform the calculations, let's so this we can, I'm going to write it here. We have gradient is equal to, this is going to be minus 2 divided by 3, and this will be 1 into minus 1 plus 1 into 0 plus 1 into 1, and then in the lower row we have 2 into minus 1 plus 3 into 0 plus 4 into 1, and thus we get minus 2 by 3. We have, and then inside here we get, this is going to be minus 1 plus 0 plus minus 1, so that becomes 0. So that will be 0, and then down here we get minus 2 plus 4, so that becomes plus 2. And if we multiply these in the final output, what we get is 0. And in the second term we have here, that will be 2 multiplied by minus 2 by 3, and that gets us, finally we get 0, and this is going to be minus 4 by 3. So those are the gradients that we have calculated, and now we can use these gradients to update our value of theta. And to do that, we would write theta is equal to theta minus alpha into gradients. And for the theta, we already have the initial values of beta 0 and beta 1, which is here. That was equal to 1 1. Then we have our alpha that we set to 0.01, so that is here 0.01, and we are going to multiply that with the gradients. This is 0 and minus 4 by 3, so I'm going to just calculate what that is. Minus 4 divided by 3, that is 1.33. So let's write that down here, 1.33, and with a minus sign. Now when we perform this calculation, we have 1 with this, and let's leave this as is for now. This, when we multiply it, it becomes 0.01 into 0 is 0, and down here 0.01 into 0.0133 would be 0.0133, and we can then perform the subtraction. So let me just check that multiplication again. So that is correct. And when we perform the subtraction, the first value stays 1 because 1 minus 1, 1 minus 0 is 0, 1 minus 0 is 1, and then the next one is 1 minus 0.0133. So that will become plus. So we have a minus sign in here, and so when we bring that out of the brackets, it will become plus. So this simply would be 1.0133. So this is the new value of beta. So that's our new beta 0, and this is our new value of beta 1. So as a next step, then the idea is to take these values of beta 0 and beta 1 and use them in here and perform the entire calculation again, get the new value of theta, and repeat the entire process. So that is how uh, we can update the values of theta to update the value of update the predicted values to get the final answer. So what I'll do is do this one calculation up to the predictions, and then we'll stop. So this is going to change, and then this is going to change right here, and that is going to change the predicted values, and it will then change. Hopefully the error might be a little less, we'll see. So the new values that are here, let's use a different color for that. Let's continue to use a red color. We have 1 and 1.0133. So these are the new values, and when we perform the calculations here, we have 1 multiplied by 1 is 1, and then we have 2 multiplied by 0, 1 point. So I'm going to do the calculations here on my calculator. We have 2 times 1.013, and then we add 1 to that plus 1, that equals 3 point. So this comes out to 3.026, and the next value is 3 multiplied by 1.013 plus 1, that gets us 4.039. And then the last value is 4 multiplied by 1.013 and then plus 1 to this, we get 5.052, right? And then these values, we are going to use them here to calculate calculate the error. And so this is, so let's see what this comes out. We have 2 minus 3 3.026, that gets us minus 1.026. Then the second one is 4 minus 4.039, that gets minus 0.039. And then the next value is 6 minus 5.052, that gets us so this is the only positive values, 0.948. So so this is what we have in terms of error. Again, then as a next step, this error would come here. We would update this term, calculate the new set of gradients, and again update the values for beta 0, beta 1, and repeat the iterations as we go through. So that what we just did was the second iteration that we started. Right. So that was it for this video. I hope in this video you got some intuition about uh, how to perform these calculations manually. And if you uh, uh, want to write a code to perform these calculations, you could watch the code switch video. Please let me know in the comment section below if you enjoyed watching this type of videos where there is some math that I'm trying to solve on the screen. And if you do like these videos, please give it a thumbs up, and I'll try to create more videos of these types. Uh, and your support means a lot. It helps me stay motivated to create more content like this for you all. Thank you. Please like, share, and subscribe. Hope to see you all in the next video. Until then, happy coding, happy math, and hope you continue learning more about data analytics and machine learning on this channel. Bye for now.